Good afternoon, everyone, and thanks for joining us today as we bring you the latest in grape and wine industry research in our ongoing 2018 CCOVI Lecture Series. This afternoon, I'm pleased to present our speaker, Dr. Jim Willwerth, who is our senior viticulturist here at CCOVI. Jim earned his undergraduate degree at St. Mary's in Nova Scotia, completed his PhD here at Brock University. And here at the Institute, he performs research and outreach services in the field of viticulture with emphasis on grapevine winter hardiness and the priorities of the Canadian wine industry. His current research interests include grapevine cold hardiness and freeze protection first and foremost, and also novel bird deterrence and clone by rootstock evaluations for the Ontario grape and wine industry. Today he'll be speaking about the use of abscisic acid and its potential implication on grapevine cold hardiness. Please join me in welcoming Dr. Jim Willwerth.
Thank you, Andy, for your kind introduction. Welcome everyone here in the room and watching online. To any of my colleagues out there, thanks for watching. So today I'm talking a little bit about some of the research that we've been doing over the last number of years through some collaborative efforts and ways to help improve dormancy and cold tolerance in especially sensitive vitis varieties. As well as try to gain more of an understanding in terms of how ABA, what role ABA can play in terms of dormancy and hardiness. So first of all, I just want to start with my acknowledgements and all the people that we've been working with over the years. We have some current research that's being funded through the Ontario Grape and Wine Research Incorporated here in Ontario. We've had some funding through OMAFRA and through the OVIP program, as well as directly through industry partner with Valent Biosciences. Now, I got into this work through some collaborative efforts in terms of cold hardiness research across North America. And one of the individuals that helped network us was Dr. Pat Bowen at AFC in Summerland. And she introduced me to some of the folks doing work with ABA, including Dr. Abrams, as well as some of the connections at Valent with Peter Petracek and Derek Wooler. So this has led to some collaborative research efforts I'm going to talk a bit about today. Currently, I'm working in that OGWR funded project with Sue and Jerome from Mabazine, as well as Randy Purves at University of Saskatchewan. So I'll talk a little bit about the work we've been doing through with all of these individuals and what we're currently up to in terms of the project and some preliminary results. So first of all, I just want to give a bit of an overview in terms of the relevance of this work and how this work can fit into what agriculture is dealing with worldwide. And freeze injury is always a threat to agriculture, especially with perennial woody plants. And grape and tender fruit being high value crops, it's a real issue, especially in Eastern North America, Pacific Northwest, even California, northern parts of California can have issues. And we're seeing more impacts across Europe as well. And a lot of this is due to the climate change and how climate change can impact many impacts of agriculture. But one of the areas that is not highly focused on really is what are the impacts of climate change during dormancy. We talk about warming influences and, well, yeah, we're going to be able to grow better crops and have longer growing seasons and have better quality. Well, if these plants have to withstand the winter and get through the winter months, having extremes during this period of time can have detrimental effects. And really, when we talk about farming, it's always about farming the extremes. And agriculture, one of the biggest challenges I think for agriculture coming up is extreme events and volatility. If you look at the moving average, what have you, it might show it's warming, but it's those peaks and valleys that can cause a lot of problems when you have temperature extremes. Because all it takes is one cold night to wipe out an industry for that year. for example, in the grape or tender fruit industry. And we've seen that here in Ontario and other parts of North America over the years. So we see this is just a chart here, or a figure, I should say, in terms of changes with climate. And we see a general warming effect, but we can also find cold effects too, where these polar vortex types of incidences, which can bring cold weather all the way down to the southern part of the US. And this is just an example of how jet streams, and when you look at how the jet stream can change with changing climate and ocean temperatures and so on and so forth, warming polar ice caps and so on, like melting of the ice caps and so on and so forth, we can have these instances where this cold surge of air moves way down into the south, and the jet stream can shift further down, and it can stay there for a long time. So not only can we deal with freeze injury due to acute, just really cold temperature for a short period of time, but also chronic injury due to just prolonged cold, and the tissue basically just dehydrates and the cells die that way because it cannot. It has issues with chronic stress as opposed to acute stress. And this is something that we could see in a really cold year. This was Lake Erie in 2014, 15. And we're seeing that most of the Great Lakes were completely frozen. Ontario had some open water, but most of the lakes, including Lake Erie, was 90% frozen. And this is just an example of what that bay there in Fort Erie looks like. And we had some good ice, and we had some polar vortex type temperatures this year even, and we had some good ice. I was out ice fishing last week, and we had 8 inches of ice out there. Now, it's not open like this, but it will be soon. And so we can go from one extreme to the next. And in general, there was a lot of talks last week, and it was a concern where we're having extremes, not only long periods of cold, but we're also having warming events. And then that's followed by cold, and that can have detrimental consequences. When you have these warming periods, and this is what we're seeing in Europe, for example, we're in places like Alsace, bud break is getting earlier and earlier, harvest is getting earlier. We're seeing an effect on wine styles already in those regions. A lot of traditional winemakers or wineries there that have been around for hundreds of years, they said that they're seeing a huge problem with early maturation, early bud break, and so on. And this can lead to consequences. Well, what's a consequence of having, bud break 2 weeks earlier? And that is the last date for spring frost hasn't really changed over the years. And so what's happening is we can have these extreme events after post bud break. We have an earlier bud break, and then we have these sharp freezes. And this is an example in the last couple of years, last year included, where some of the regions were frosted out. And a lot of northern France had frost issues last year. France reported that they had about €2 billion loss due to extreme weather, a lot of it cold related, but also Burgundy has not only been hit by frost last year and some other years, but they've been hit by hail, I think, I don't know how many years in a row, which, as you heard, a really important wine industry for France, but also in terms of its hardiness, how it's a dynamic condition. It's not static. It's not as soon as the vines lose their leaves or the plant loses their leaves that they're automatically at their maximum hardiness. It's dynamic in nature, and it goes through three phases: the acclimation period, where the plant is gaining cold tolerance, maximum cold tolerance in generally the early part of the winter months, and then this period of deacclimation. Now, these are driven a lot by temperature and the environmental conditions, that in the grapevine, or the plant's genetics, I should say. And so the temperature influence can have a huge impact, particularly in the deacclimation phase. So when we have warming periods during the winter months, it can really cause the plant to lose cold tolerance. This is followed by a cold, sharp drop in temperature. The plant might not be ready for that extreme and cold, and it could suffer some damage. because of that. And we've seen this over the years. And different regions have different threats in terms of, in the Pacific Northwest, a lot of times they get a lot of early freeze events, and they can be more susceptible during the acclimation phase. For us in Ontario, we generally see our damage more in the maximum hardest period, as well as during the warming periods during deacclimation. So later in February, where we are right now, into March, we've had some real significant events in the past. Now, when I was talking about how it's dynamic, here's just an example through some of our outreach programs. This is through our vinyl program, where we're monitoring the same vineyard, the same varieties, the same locations over the last, in this case, 9 years. And you can see how it can differ in terms of how the vine is acclimating. Maximum hardiness can vary from year to year, but particularly the deacclimation period can be highly variable. In a cold spring, this was a very, very cold year. There was that year that showed that picture of the lake being completely frozen and the Great Lakes being frozen in general. And you could see we got off to a really late start, and the vines were much more hardy in this period of time than, let's say, 11, 12, where we had that real abnormal weather and it was extremely warm. We broke records for the month of March and end of February. Whereas there was the other extreme in 13, 14, where we had one of the coldest Februarys ever. So it can be highly variable. And you cannot just say on a certain calendar date that the plant is hardy to this particular level. So like I mentioned, the warming during the time when the plants are held in dormancy through cold temperature stresses generally is the time where we're really concerned with, and where this erratic winter temperature can really come into play. If we have a lot of extreme temperatures during acclimation, the plant cannot break dormancy at that point. It's endodormant, so the temperature effects don't have the same effect. But when we get later into the year, these periods of warming followed by extreme weather can have devastating consequences. And this is just a year. I just wanted to put this data in. It was similar to that first graph I showed you, where we had all 9 years. But in this case, what I've done is I've just taken out the years where we've had very cold winters and then very warm winters in really warm late winter, spring periods. In this particular year, we've had really wet conditions. We had larger or more vigor this year, more rain, and a combination of all of those factors led to less acclimation in the fall period. And even during the cold months that we've had in January and end of December, the plants still did not acclimate as well as they have in other years. And as a consequence, we're now seeing that we might be on the verge of having early deacclimation, similar to some of those years where we've had issues with freeze injury in the spring, particularly in tender fruit. So we're keeping an eye on this, and we had temperatures above in double digits last week in terms of, we had some highs of 13 degrees one day and lows of 11 degrees. So that's not good in terms of keeping the plants dormant. So what are some things that we've been doing and people have been doing to help mitigate some or potentially mitigate some effects of these factors and what climate change can bring? And one of the tools is plant growth regulators, and they're commonly used already in viticulture and horticulture worldwide. In terms of grapes, they're used quite consistently in warm regions and hotter climates, particularly in table grape production, and in areas where there's tropical viticulture, areas like Brazil and so on, which are becoming larger grape producing areas. And these PGRs, or plant growth regulators, they serve various purposes based on what you're trying to achieve. And it's basically just looking at, if you look at the nature of these PGRs, each one has a different purpose in terms of grapevine development or plant development and so on. But right now their use is really limited in Canada. They're used in the US and other parts of the world for viticulture, but not so much in Canada. So it's kind of a new thing that we're exploring here in terms of Canada. So just in terms of grape cultivation and just some examples of some different plant growth regulators and some of their uses, We have the gibberellins, which are used highly in the table grape industry for improving cluster appearance and morphology and so on, looking at cluster elongation, berry sizing, and so on. And those are generally sprayed earlier in the season, pre-bloom, bloom, just after fruit set. Same with the cytokinins. They're used for berry sizing, for example, and that's after fruit set. And then there's a couple other plant growth regulators that are used widely for color improvements. And sometimes it's multiple applications of these to serve the purpose. So in some production, there may be, it might be using gibberellins early and then actually going through this entire cycle of using PGRs to get the product you want, especially when it's table grapes and you want that appearance. I still remember in Dr. Reynolds' course, in grapevine biology, he had a whole section about life of a table grape farmer, and the question was like, okay, what would you apply and when would you apply it and so on. I see students, former students nodding in the audience, and it really just drove the whole idea of how hormones work in the plant, but also the practical nature of using these things. And that's where some of this research now comes into play. Now, in terms of abscisic acid, because that's what I'm talking about today, it's an isoprenoid plant hormone. It's found in all plants. It regulates a wide range of processes in plant growth and development. Traditionally, it's a stress hormone that responds to abiotic stress. It's involved with transpiration and is involved with responses to heat, drought, salinity, and freezing. A lot of it has to do with water in terms of its purpose and regulating water within the plant. In terms of growth and development, it's really when you have the cytokinins and gibberellins and so on, which are involved with growth. ABA works in contrast to those and more on inhibiting growth and senescence. And also, it's really important in terms of secondary metabolism and secondary metabolites and the production of all those goodies that you get in grapes and so on. Its use has also been used, especially commercially, in terms of seed development and seed and inhibiting seed germination and so on, especially in some really important, in Canada, like in legumes and so on. This is where a lot of the work has come into play, is looking at how ABA can be used for that purpose. In terms of cold tolerance, I just put one slide in here just to put it in perspective of why we are looking at ABA in terms of improving cold tolerance and so on. One thing is ABA has been known to enforce dormancy in the plant, and that's also inducing dormancy, but also maintaining dormancy during periods of higher cold tolerance. Generally, ABA levels are higher in the tissues versus in periods where the plant is coming out of dormancy. Induces expression of genes, and is really, and I'll show the next slide quickly, in terms of how it protects the cells from dehydration. So it's a stress hormone, right? So it's one of its key roles is protecting cells from dehydration. One of the newer areas of research where they're finding more and more information and data concerning how it's working and interacting with other signaling molecules, particularly when it comes to regulating cold tolerance responses. So signaling molecules such as calcium, nitric oxide, hydrogen peroxide, and others. So there's an interaction there in terms of signaling. 2 weeks ago, Dr. Nassuth talked about some of these transcription factors and the CBF genes and so on in ice. ABA can impact expression of the CBF genes, as well as induce dehydrin gene expression, as well as accumulation of some of those cold regulated proteins. Now, there's ABA dependent and independent pathways. In a lot of the years, some of the research has been confounded a bit because of using ABA and using racemic mixtures and so on and so forth. So we're trying to tease out more of the ABA effects in terms of dependent and independent pathways. But because there's environmental and abiotic conditions involved with cold tolerance as well as a lot of stress, it can be quite complex, and it's not just it's not a real easy peasy thing to study. And this is just an example. I'm not going to get into this too much, but there's just it's quite complex here in terms of some of the cold and dehydration responses. But the ABA dependent pathways are a lot related to dehydration, and dehydration kickstarts a lot of these ABA dependent pathways, whereas cold, and what Dr. Nasuth was talking about last week, cold is involved with, and cold temperature stresses starts to trigger some of these ice CBFs and so on. And then ultimately we get that cold stress response. So we're learning more and more about these interactions and these complex relationships in terms of ABA and cold hardiness responses. Now, in terms of ABA used as a plant growth regulator, there are a few commercial ABA products on the market. Part of the issues is with ABA is that they do have a short half-life in plants. They're turned over quite rapidly in the plants to inactive metabolites. And like I said, this is a stress molecule after all. So the plant does not want to have these kicking around for a long period of time. They want to alleviate that stress and get on to business. Just like with us, our sympathetic nervous system, there's a lot of hormones involved with kickstarting that, for example. And you don't feel good when your body's under that type of response. And so the plant does not want to keep these hormones active for a long period of time. Another limitation is it can be light sensitive and inactive in sunlight. So as well as just natural ABA, ABA analogs have been studied and synthesized and studied, and this has been part of the work that's been done in the Abrams lab over the years. And these analogs can be more effective than natural ABA for improving cold acclimation, and part of it in other purposes as well. And part of that reason is that they do catabolize more slowly in tissue. There's been research to demonstrate that, and as well as they maintain high bioactivity. And so when these compounds, molecules stay in the tissue for a longer period of time, you can have prolonged and enhanced effects, especially on dormancy and hardiness. And I'll explain a little bit about the research that we've been doing over the last number of years. And here's just an example of what the structure of natural ABA is compared to one specific analog, which has probably had the most work published on it, the 8'-acetylene ABA. So in terms of some ABA and ABA analog research, I just want to put into context in terms of some of the connections and collaborations that we've had over the years, and just put this into a bit of context, is that Sue Abrams, Dr. Abrams and her lab have done research at NRC, at the Plant Biotechnology Institute in Saskatoon for many years. She's now at the University of Saskatchewan. They've been looking at analogs for plant growth regulation, doing a lot of research with ABA metabolism, identification of ABA receptors and binding proteins, as well as a lot of method development in terms of hormone and catabolate analysis. So we're working with her group now to help understand more about some of the research that we're doing. Now, in terms of some studies that have been done with ABA in the past, with ABA applications and as well as the analogs, there's been some work done to look at improving drought tolerance using these molecules, thinning of crops, particularly apples, improving color, hastening maturity in fruits. A lot of work done in the warm areas of table grape production in California, and as well as inhibiting germination in seeds and so on in Saskatoon. We've been looking at doing some dormancy studies and maintaining dormancy, and that's been done as well in terms of seed production. So in terms of what we've been doing over the last 5-6 years, when we first started this, was looking at a novel approach to ABA in terms of using ABA as a foliar application to improve hardiness, as well as better understand the role of ABA. So this work has been conducted over the last number of years with our cold tender varieties, with Vitis vinifera varieties, and we're looking at regions across North America where freeze injury is common. Here in Ontario, Pacific Northwest, such as BC, Washington, including Idaho, as well as some work in Ohio. There's also been some work done in Colorado as well. And a lot of this work has been, like I said, collaborative in nature. And when we first started doing some of the experiments, it was a collaborative effort between Ontario, like I said, Ontario, BC, Washington, Ohio, and Idaho, but also a collaborative effort between the Abrams Laboratory and Valent Biosciences. So Valent Biosciences has a commercially available ABA. It's a natural ABA form, trademarked under the name Protone. And so we were looking at using that because on the label of Protone doesn't say anything about improvements of hardiness and dormancy or what have you. So looking at that commercially available formulation and also looking at some of these analogs. So the first study I just want to talk about is the one we did with Med Dami out of Ohio State University. He's done a lot of work over the last number of years looking at natural ABA and using it to improve cold tolerance. So we did this study in 2012-13, I think. and it was basically, we looked at 4 distinct grape growing regions, Ontario, Idaho, Ohio, and BC. And we looked at 3 different time periods at the same concentration of commercially available ABA. And the time periods we looked at the applications were vrazin, post-vrazin, and post-harvest. And for this study, what we did was we used the same variety across all regions, and that was Chardonnay. We then looked at hardiness, we looked at timing of bud break, yield components, fruit quality, and so on after the fact. So I'm just going to, in the interest of time, I'm just going to show you some of the results that we found here in Ontario, and I'll talk a little about the summaries of the whole study. Now, what we found with the natural ABA was that we found improvements during the acclimation period. So especially early in acclimation, within the first couple of weeks of applications, we found that there was some improvements in terms of hardiness with the ABA, the natural ABA, up to 2-3 degrees in some cases. But across most of the regions, what we found was that there was a lot of inconsistency later in the dormant period and during deacclimation. We didn't find any delays in bud break, and some regions had more profound effects in terms of acclimation as compared to others. In terms of timing, generally speaking, the vrazin, post-vrazin applications were the best, but again, there was a lot of inconsistencies, and this is just one example of just here in Ontario of how there were some differences for the timing of application as well. So overall, we found that there are some inconsistent effects for timing as well as the regions. They are distinct growing regions, and I'll get a little bit of that later when I talk about the next study. And that could have some impacts in terms of how these applications worked. In terms of improving cold tolerance, out of 3 of the 4 regions, we found that it did improve we found those improvements during the acclimation period. But no real improvements or consistent effects, particularly midwinter and during the deacclimation period, the times where you can have a lot of that volatility in the weather, and it could be really important to maintain dormancy. So we didn't find a lot of maintenance of dormancy using these natural ABA. The next study was one that we did kind of simultaneously, and this was done using Merlot with colleagues in BC again, Idaho, as well as Washington State. And in this case, we looked at different forms of ABA, different concentrations. We looked at some application timings as well, and looking at how these analogs might differ in terms of the natural ABA. So we looked at, again, 4 different regions, except we didn't have Ohio in this one. It was Washington instead. And then we looked at these different forms, concentration, and timings of ABA and its analogs. And the same thing, we measured hardiness, we looked at bud break and phenology, as well as yield and fruit components. And this is just an example of some of the effects that we found. In the first year of the study, this is here again in Ontario, and it's hard to see because I just crunched the figure actually from the paper and onto this PowerPoint slide. But we didn't find a lot of improvements during acclimation. But later in the year, we found a lot of improvements in terms of maintaining dormancy, as well as, well, I guess it would be maintaining dormancy. So it was improved cold tolerance later in the season. And this was mainly due to the analogs. Now flip it to the next year, and we had the similar effects with the analogs helping to improve and maintain dormancy late in the season, particularly when we've had some warmer conditions, but also we found some improvements during acclimation, and these were related to both the analogs in some regions, but overall a lot of the natural ABA seemed to also improve acclimation during the or cold tolerance during the acclimation phase. So it was really interesting to see that the analogs seem to help later in the season and help, and I'll talk about in a second, delay bud break, whereas the natural ABA seem to have that immediate impact with acclimation. Now in terms of delaying bud break, what we found was that in some cases and in some regions, we had delay of bud break in some cases. Now I talked about, we had that one, or showed that graph with, we had really early deacclimation and early bud break that caused a lot of freeze injury in here in Ontario. Well, that was 11-12. And this is bud break in April, end of April 2012, which is really early for us to have bud break. And this was Merlot. And Baco Noir, for example, in Chardonnay, we had bud break even earlier than that, up to like 2 weeks before this even. But what we found was that the control vines had almost 100% bud break getting into that time of year, whereas some of this 30158, these were some of the analogs, and we found they had significant delay in bud break compared to the rest, even including the mixture. We had one mixture with high concentrations, and that also had the effect of the analog. Now I'm not sure how well you can see it here, but in this bottom left is, you could see these vines, the bud break was so early that the block hadn't even been pruned yet. We were still collecting samples, so we left them unpruned. But you can see, I'm not sure how well you could see it, but this is the control where we see bud break on pretty much every bud is broken, whereas this vine still looks completely dormant. So it was really interesting. But in a normal year, let's say a normal winter, we didn't find any differences really in bud break, which was an interesting find. And we found that in different regions as well. Some regions had more of an effect on delay of bud break than other regions. This was in one of the years in Washington where we had the delay in bud break with the higher concentration of analog. But what we see is that it did slow down the development, growth and development of the plant. But by the time the berries were pea size, they were on equal timing of growth at that stage. So we had some early delay in some of the phenological stages, but ultimately they caught up to each other, which was an interesting find. And we found that here in Ontario as well. So in terms of some of the findings of this study, we found that the natural ABA, especially at higher concentrations, what it did was we found some improvements in hardiness, just like the study with the Chardonnay. However, the results were more inconsistent with the natural ABA, and we had no delay in bud break using any of those treatments, even at the higher concentrations. The analogs, which we hypothesized would be the case, would be more consistent and had a greater impact on improving acclimation, particularly late in the winter, so that helping maintain dormancy. And we found that the effects of ABA analogs also had that delayed in acclimation and bud break, particularly in that really warm, extreme year, which is interesting because it seems like the more extreme the conditions are, the better they work in terms of holding that plant back. And in 2012, we had a delay in bud break of over a week. But again, the application results and benefits may vary depending on the season as well as the growing region. And part of that has to do with the nature of how the grapes are cultivated. In the Pacific Northwest, for example, in BC and Washington, it's very arid, a lot of deficit irrigation, whereas in Ontario, for example, we have cooler, wetter growing seasons as well, particularly during harvest. So those can create differences in terms of ABA within the plant and so on and so forth. So what are we up to now? We're currently looking at more work concerning these long-lasting analogs. And we've collaborated with the Abrams Laboratory again in University of Saskatchewan. And in this case, what we're studying now is that same analog compound, but also another form of ABA analog. And again, we're comparing it to natural ABA. So right now, we're field trialing these exogenous applications in two varieties, both cold sensitive, and some of our problematic ones here in Ontario for winter injury, and that includes Sauvignon Blanc and Merlot. And we're looking at measuring the impact on dormancy, cold tolerance, bud survival, and looking at, again, phenology, particularly bud break, and seeing what kind of delays in bud break we can get. And we're getting more and more interested in terms of maintaining dormancy and prolonging timing of bud break or delaying bud break because of these warm weather conditions that we're seeing. If we can keep the plant a little bit more hardy, especially during these warm periods that we're experiencing right now, even, that could be an advantage. So we're also looking at the biochemical analysis within the tissues. We'll want to look at the endogenous levels of ABA and also track analog within the tissue and look at other hormones and other catabolites. So that's another added thing that we're doing here. Just some preliminary data, just to tease you with, I guess, is we've been out testing the vines for their cold tolerance after applications this particular winter. And during cold acclimation, what we found was, just like in some previous studies, the natural ABA, which is at a higher concentration here, we're getting some benefits in terms of improvements in hardiness. But what we're finding is that these analogs, these are two different compounds, the 1016 and the 1017, they're improving cold tolerance quite a bit in terms of acclimation. In LT50s, we're getting up to 2 degrees improvements in hardiness. And LT10s, I just want to point that out. This is what we use, or the growers use, in terms of when to turn on wind machines, for example. This is the period at which 10% of the buds will die, and we're finding up to 4 degrees improvements with that. So what does that indicate? That there's probably less sensitive or less tolerant buds along the cane. So we're getting some improvements overall in terms of hardiness, but also less weak buds. And we're finding that with both the Merlot at the first 2 sampling dates, as well as with Sauvignon Blanc. What we found was that just like with some of the previous studies, that leaf senescence was observed with some of the natural ABA, or with the natural ABA applications, but not so much with the analogs. And we had a frost maybe 4 days or so after the application, and the vines that had the ABA analog sprays on them looked pretty good. They were still green and looked quite nice. So if you looked at some of the papers that have been published over the years where they've looked at Arabidopsis and just put it under some freezing stress, and you see some of the ones that had ABA applied to them, they're all wilted and all buggered up. And then you see the other ones that are nice and healthy and vibrant. And you see the same thing when you look at some of these experiments that have done with tomato seedlings, Arabidopsis with ABA and drought stress. It can be quite dramatic in terms of just how they appear after just a slight bit of stress. But what we found, just like every other time, when it comes to maximum hardiness, we find no improvements using any of these ABA concentrations, formulations, what have you. You cannot change the genetics of the plant. So we can help improve during the periods where they're gaining cold tolerance, and it seems we can get some improvements, hopefully, and especially with this weather, with deacclimation and maintaining dormancy. But in terms of maximum hardiness, there's nothing you can do really to help. If the vine's in good shape to begin with, it's healthy. By applying ABA, we have not seen much improvement at all, or any consistent effects during maximum hardiness. So what's on the agenda for the future? Well, right now, in terms of current status, we're continuing to track the cold tolerance up to bud break. Like I said, we've had some really warm weather, so we're excited about the season that we've had, because we've had some extremes we had some cold weather during acclimation, which we normally don't see. to the same level of cold that we had this particular year. Then we had some cold midwinter temperatures, and now we've had some warming events where it's been particularly warm. So it's going to be really interesting to continue to track cold tolerance and see what kind of impacts we have on bud break and what have you. We've, at different time points, we have sampled tissue, freeze-dried it and everything. So that's looking at all this ABA analog and catabolate analysis. That's going to happen once this year is concluded. Look over at carryover effects such as yields and so on, and fruit quality. And then further research in terms of analysis and other collaborations, looking at maybe expanding this into tender fruit. Apricots, for example, there's interest in because they're such a pain in the butt to get through the winter, and because of their susceptibility to spring frost. So we're interested in expanding there, and as well as maybe looking at some growing season applications. But right now we're focused on this research and those first 4 points there. So in terms of conclusion, the ABA as well as analogs may be a powerful tool to mitigate climate change risks. And through some of the work, it seems that some of the formulations may be more suitable to certain regions. Areas where we have a lot of fall frost and fall and early winter freeze injury, the ABA, natural ABA may be the one you want to use, whereas the analogs seem to be persistent in the tissue and maintain, well, we don't know, we'll find that out, but they seem to be more maintain dormancy, and we're trying to figure out exactly why that is. And so in areas where we have freeze injury risks during deacclimation and due to early bud break, they might be a powerful tool to mitigate those risks. And that includes areas that we're in across the world where we're finding more and more spring frost injury that's having massive effects. So these can help, again, improve and reduce freeze injury, whether it's enhancing dormancy and improving acclimation, or maintaining dormancy and helping to reduce those late winter freezes. So, but like I said, form, concentration, and timing can matter for the desired effects that you want. But again, there's still a lot to know. Are there some benefits of slowing early development? Perhaps, particularly as cool regions are becoming warm and warm regions are becoming hot. We might have more and more of a use of using plant growth regulators and using something like ABA to help, which traditionally hasn't been used for this purpose, but potentially to help slow things down. So we're not having regions that have been growing grapes for centuries and they've adapted to those regions. All of a sudden the region changes and those vines cannot produce the same quality of fruit that they have for hundreds of years per se. And big problem in the wine industry is high alcohol wines, and this is one of the impacts of climate change. So what can be done to slow them down? This might be a solution in some areas, but we'll see. So there more to learn, and there's from both on the fundamental side of ABA and cold tolerance, but also the practical side here as well. So I think this will keep me busy for a little while. And it's been interesting because we're also trying to dovetail this research into existing cold hardness work that we're doing. And so hopefully learn a lot more over the next little while. So thank you very much. And thank you to all my colleagues.
Well, thanks, Jim. And do we have any questions? First from the audience, and then afterwards we'll ask anyone that's online whether they have any questions. Yes.
Besides looking at the cold hardness and dormancy, are there any trade-offs for plant health? Because you mentioned that analogs tend to stick around in the tissue longer. And are you looking at anything, or is there anything that you can foresee being a consequence of that to the plant?
Well, the obvious consequence is, the question was, are there consequences of the analogs because they maintain bioactivity and more persistent in the plant. The main disadvantage, probably a consequence, would be that delay in bud break, particularly if you are in a region where you have a very short season and you need to get those vines going as quickly as possible. And that would be a region that wouldn't have an early or a late spring frost risk. If there is a spring frost risk, then delaying bug break probably is advantageous. In terms of the work that we've done, we haven't seen a lot of negative consequences from carryover effects from year to year. So, but we're still doing more of that work, and again, different regions, different varieties, and so on.
Great talk. I was just wondering whether the ABA analogs were light sensitive as well, and how frequently you had to apply that to get the effects that you see.
Yeah, I think they're probably, I don't know for sure actually. I should ask Sue about the light sensitivity of the analogs, but that's one of the biggest problems with ABA is actually getting it into the tissue. And I think that's one reason why there's inconsistent results. The natural ABA seems to be more problematic in terms of inconsistencies and trying to deliver it into the plant. But with some of the tissue analysis that we're doing, we want to see exactly what's getting into the plant itself and learn more about that. And I think once we do that, we have a better understanding of maybe how susceptible the analogs are, but I'm sure Sue knows. I don't know personally. Anyone else? Anyone online have a question?
This is Pat Bowen. Can you hear me?
Hey, Pat. I can hear you.
Hi, Jim. Excellent seminar.
Thanks.
Really enjoyed it. I had Carl here with me as well. We really enjoyed it.
Good.
Really
Thanks.
great to see you moving ahead with this work. What do you see as the biggest challenge to refining ABA as a tool for the industry? And I'm thinking about what you were just talking about, this inconsistency in response, and it's sort of annoying to see some years it works so well and others maybe not so well. And are you focusing any of your new work on trying to get more of it into the plant or increase that consistency?
Yes, that's one of our objectives, is to look at optimizing the applications. So right now it's still kind of that proof of concept, especially with that new analog that we're trying out this year. And then our hope is to look more about optimizing the applications, so we know what's getting into the plant, and then to try to find ways to improve consistency, to see is it a timing issue? Ahmed published some work looking at leaf age and so on, and looking at those aspects. As you know, with the PGRs, the timing and the stage of the plant is really important. So we're trying to look at some of that and trying to optimizing the uptake into the vine. Does that answer your question?
Thank you.
Does that answer your question?
Yes, it does. Thank you.
Okay. Thank you, Pat. Thanks for listening. Anyone else? Okay. Thank you.
Oh, good. Sorry. Did you see a dose response out of the acclimation of RG other than late season with either the natural ABA or the analogs? Or was there sort of a minimum amount that was required?
Oh, yeah. That's the other thing we're trying to look at, is what's the minimum amount we can apply to get the desired response.
Okay.
So that's another thing we're looking at right now. In terms of the natural ABA, the higher concentrations had more of effect for acclimation for sure. With the analogs, one of the advantages of them is you can use a lot less of those molecules compared to the natural form. So that's a huge advantage. It's just, especially for a cost factor. Unfortunately, upscaling the synthesis of these analogs is another challenge, but that's for my colleagues to focus on. But we're looking at what's the minimum rate basically that we can use, obviously for economic benefit for the grower.
Okay. Thank you. Well, Jim, on behalf of COVI, thank